Hey, welcome back, Data Junkies. Your host, Shawn Janzen here, as we're continuing our talk about Z and T tests in the realm of two-sample hypothesis testing. I'm completely excited to be here, but I'm going a little hoarse, and I gotta keep making the videos anyways, so please bear with me, and I'll redo this video for you when my voice is feeling a bit stronger. But otherwise, let's go ahead and get started on topic 9.7, talking about effect sizes for the Z and T tests, two-sample hypothesis testing. And this video is going to focus specifically at effect size. I'm going to have another one in which we talk a little bit more about power, and we're really going to start going into some visual representations for it. So again, just to do a brief effect size recap, significance is not the same thing as importance, and we have different types of significance. We can have things that are impactful and meaningful and sizable and substantial that have nothing to do with its generalizability to the population or not. And these are the things that we call substantive significance. These are the things that are captured by effect sizes. Whereas when we're talking about statistical significance, these are where we're talking about things like alphas and p-values, scores obtained and critical values. Can we take findings and generalize them to the population? And what I want you to take away with some of these things when we're thinking about effect sizes is that the larger the samples you get, the more likely it is you might get statistical significance if there's significance to be found. And even though you get statistical significance, it could start triggering even though we might have very small effect sizes. So there might be very small differences in the things that you're comparing, but they're still saying that they're different enough that we can generalize our findings. So just be aware that as we go looking into our different versions here. So what we have here on this slide are an effect size flowchart where I show you that the effect sizes, we have two kinds, unstandardized and standardized. And the unstandardized are relative differences in means and proportions. These are things that still keep their units of analysis if it's measured in pounds or dollars or number of dogs, right, or how many friends you have. So these are things that we can still measure and count on the same units of the things that we're comparing. But it doesn't allow us to compare to other things that we might want to compare it to, such as if you want to compare box office dollars from one movie to maybe box office dollars of another movie. It might depend on things like our standard deviations might throw them off. So even though they're both movies and revenue, they're difficult to compare. So in that case, we would need to standardize it. And actually, when you standardize it, you could compare it to anything as long as it has that same effect size type. Like we talked about Cohen's D before, we're going to talk about Cohen's D again. So Cohen's D of one thing can be compared to anything else that's a Cohen's D. But we standardize by dividing the relative difference by a standard error of the difference. And that takes us into the standardized. And when it's standardized, we drop the units. It is unitless, and it is simply a number that represents the magnitude of significance. So moving on to this, I just mentioned that it is the magnitude of the observed results. And what you're going to need to do when you're talking about these things is report both the effect size as its practical significance and what it means by it. So put it into the context of the problem. And there's numerous measures that we're going to have of effect sizes. The most common of which that we're using in this module here is Cohen's D. It's a standardized difference for two means. We've had it with the one sample, and we're going to use it again with the two sample. So just keep in mind that when you're using effect sizes, relate it back to the scale of the outcome. Think about your audience. Think about the messaging and the content that you're working on. Don't just say, my effect size was 0.04 and it is medium. Okay, big deal, so what? Put it into the context, right? Are we talking about the number of wrestlers that were thrown out of a ring, or the number of new anime that have come out this season relative to the number that came out in the past 3 seasons? So put it into the context and suit your audience and flavor when you're dealing with these things. It'll help make things much more intuitive for both you and your readers. Now, let's talk a little bit about the different types of effect sizes. We have different calculations for different circumstances, depending on the different types of analyses that were performed, ratios, sample size variances, etc. The most common kinds are for the independent t-tests, and so we could use the unstandardized means difference. That's oftentimes it happens in medical research and anything really that you're just comparing groups together. And you have the standardized difference, which is where we include the standard deviation. That's our Cohen's D. You can also have the mean difference with pooled estimates, and you can also have confidence intervals. All these are different ways of helping to get at effect sizes. But let's move into Cohen's D. Now the formula here for Cohen's D is a little bit different than what you saw before, because this is accounting for our ability to have two samples in place. So the Cohen's D is equivalent to 2 times your t-score that you get from a t-test divided by the square root of n, which is also approximate to the x bar of group 1 minus x bar of group 2 divided by the square root of the variances of group 1 and group 2 added together divided by 2. So we have this pooling effect going on in the denominator before we divide it into our difference in means up top. And that's going to generate a Cohen's D, where we're going to use the supersizing french fry size chart. Now we've got small, medium, large, very large, and huge. So small, 0.2, medium, 0.5, large, 0.8, 1.2, very large, and American size, supersized fries, 2.0, huge effect, right? Again, I recommend you make yourself a little cheat sheet because we're just going to be adding on more different effect size tests as we go, and just make a note of what the effect size name is, what you use it for, and then what the numbers are for your french fry size tool here to help you see these out. Well, what you don't want to do is start using the ranges for phi and Kramer's V when you're talking about a Cohen's D, because they're different french fry size numbers. So, moving ahead a little bit, we also introduce Hedge's G. Hedge's G is just like Cohen's D, except it does a little bit of a tweak in the denominator when it's pooling data for small numbers. It's weighting the pool based on its standard deviations on small sample sizes. So, the way you go ahead and get each of these, Cohen's D, use it for samples larger than 20, in which case it's equivalent to or better than Hedge's G. When your sample size is 20 or less, Hedge's G tends to be the better bet. And it has an ability to correct for unequal sample sizes in the ends as well. Go ahead and check out the function descriptions for Cohen's D to see if you have a feature in there for Hedge's G or not. I'm going to introduce to you, we learned one package, the LSR, that has one version of Cohen's D. I'm going to show you another one that has another version of Cohen's D, especially for those of you that might be having trouble getting one of the packages to install. I need to also recap Cohen's H. Cohen's H here is going to be the same for the 2 sample proportions as it was for the 1 sample proportion. It's going to be using the PWR package. We're using the es.h function, except in this case, instead of using proportion of your sample and proportion of the population, we're doing P1 and P2. We're plugging those in, and it's going to go ahead and generate the effect size for us. But otherwise, the same ugly formula using arcsin, all that's still the same. But what I want to touch on a little bit now that we get into the more graphical side of things, so how does it look with these effect sizes? So you can imagine that you have this sort of null curve, right? And the null curve is saying where there's no difference on something. But we're also proposing that there's another curve, an alternative curve. Keep in mind, this whole time when we're saying that we could reject the null, it's not saying that there's no distribution curve. We're just saying the distribution curve isn't where it's at right there. It's somewhere else. And so when the Cohen's D is small, what we have is a situation where your null and your alternative are relatively close. They're overlapping. And as Cohen's D gets larger and more widespread, then the alternative curve starts to pull away and separate from the null distribution curve. So with the graphic on the screen here, we can see when Cohen's D is 0.02, it's small, they're extremely close to each other. At 0.5, they're pulled apart a little bit. 0.8, even more so, and at 1.2, we can definitely see the sort of like 2 humps emerging differences in data. So let's go ahead and talk about how you can do some of these in R. I have on the screen for you 2 different versions of Cohen's D. They'll both give you the exact same Cohen's D values, but they've got some different options under the hood here. So the LSR package version of Cohen's D, note how it's spelled with a lowercase c, uppercase d, no dots or anything in between. And you can specify it, your x and y, a couple of different ways. But you can also do things like mentioning if it's a pooled, unequal sizes with the Welsh correction or a paired version as well. With the version that's in the F size package, we use Cohen .d, all lowercase across. Also, we can put it in a variety of ways. And in this case, we have an option to ignore missing values that the other one might not be able to work with. And then we have a different way to activate and deactivate if it's pooling our variable samples, if it's a paired version, or in the version if you want to have a Hedge's G. So the version in the F size is a little bit more functional for perhaps much of what you're going to be doing, but the LSR package is also a very good one to rely back on as well. So here are 2 different versions of the Cohen's D options you can use. Feel free to use whichever one works best for you. So let's go ahead and use this as an example. In the previous videos, we had the discussion of using the Catholics versus Protestants and the number of children. And at that time, we learned that there was no real statistical significant difference between them. They both had approximately 2 children. But if we wanted to use that data anyways and just plug it in, here I'm using the Cohen D version from the F-size package. I'm specifying the number of children's variable and the grouping variable, and I'm saying that we're going to remove any missing values. We are pooling together the samples and that this is not a paired test. And what we find is our Cohen's D estimate is somewhere between a 95% confidence interval that contains a 0, which is why we're not statistically significant, and the D estimate itself is 0.02, which another little cheater feature about the Cohen's D function out of the F size, it's actually going to give you a little interpretativeness inside parentheses after your estimate. And so here it says it's negligible. It's so small, it's hardly even noticed. 0.02 is just a speck on the French fry size scale. We aren't even considered small until we get to 0.2, which is a magnitude of 10 from here. So let's see how Cohen's D can work for the pre and post assessment example that we did. This is the one where we had some student data and we were trying to see how they did before with a pre-test and a post-test. And in this case, we're using the same function, Cohen's D. We're using pre and post. na.rm equals true. We're false for pooling because we're not pooling a sample together. It's a single sample group of individuals. And we're turning on paired equals true to turn on the paired functions. In this case, at least with the Cohen's D version, it's going to give you something it calls glasses delta. Don't worry about that. Treat it just like a Cohen's D in terms of its differences and how it works and things like that. We're not going to go down the stats rabbit hole in this class with glasses delta. But note that the effect size here is negative 3.7. And it's negative just because the post was larger than the pre, which is why it turned out to be negative. Had they been flipped, this would be a positive number. So don't worry about, think of this in absolute value terms. And in absolute value terms, 3.7 is massive when our supersized American fry size of 2.0 is considered huge. So keep in mind, when it says large, it's actually very, very large. But this is also a little bit of toy data too that I manufactured to help produce that particular example. When we're talking about the space budget example we just had a few moments ago, those were proportions, and in this case we're going to use the Cohen's H for that one. So I've loaded up variables that have identified P1, P2, N1, N2, which I can use then in the version that has the arc sign transformations, and it's going to give me a Cohen's H of 0.2388 and change. But instead, I could be much better served just using the es.h function inside the power library, not have to deal with the ugly function up above. So we just plug in P1 and P2 into the es.h function, and we get the exact same effect size for Cohen's H, 0.2388 and change. And remember, we're going to interpret the Cohen's H on the same scale as we do the Cohen's D for the small, medium, large, and very large effects. And now I'm going to introduce for you another effect size, R squared. R squared we haven't talked about much at all yet, but we're going to, and it's going to become a large part of our discussion moving forward into other things, especially as we get towards correlation and regression. But R squared in this case can be an effect size for these sorts of tests because it helps just give us a single number that explains the variation in whatever it is that we're looking at. So where R was a measure of linear association bound somewhere between -1 and 1, R squared is just the square of R. But we can also generate it using a t-score in degrees of freedom, and it's probably one of the simplest ones that we can do. It's the t-value squared divided by t-value squared plus degrees of freedom. And that generates an R squared score, and we can use yet another French fry size scale of 0.1, 0.3, 0.5, and 0.6, where we're talking about these sorts of strong effects. And so just keep in mind, when you're looking at an R square, there can be also these measures of association that are between 0 and 1 as well. So I just want to leave you here on this particular chat with, again, remembering when we're talking about effect size, we're talking about how you get outcomes that are different whether you have statistical significance or not. You could be statistically significant or not. You could have effect size substantive significance or not. And that's going to give us 4 possible outcomes of what could happen in your research. So just understand which one of these 4 quadrants you're going to be in, and that's going to help you frame what are my next steps? What do I do from here? Is this something I need to get someone else's eyes on? Do I need to go back to the drawing board? And so on. And just keep in mind, you can always find some really novel findings either way you're looking at it. But I'll see you all in the next video.